Okay, here we go, folks. All right. Today I want to talk about something called resistance. Electrical resistance. Yes. Does it say do not press? That's the times button. Do not press the times button when you use the EXP. That's what's getting your incorrect exponent. Yes. Well, yes, it does. It's got to have it. I'll explain later. Yes. Don't write ahead. I'm not answering that question right now. Watch this. Look at that. Resistance. Listen up. We are learning about something called electrical resistance. What does it mean to resist? What does it mean to resist, Danton? Doesn't want to do something. Good. Yeah. Yep. Repel? Kind of, but I like Danton's better. So, yep. You can't define something with the same word that I want you to define.
Yeah. Like you really want to buy something, but you're like you can't because you're poor and you're like I'm resisting it, so I'm not buying it. Like
you still use the term resist. I like. What did you say, Danton?
It just doesn't want.
Does not want to do something. Does not want to do something. Correct. I like it. Now, listen, folks. Come on. Let's get set. Electrical resistance is when a particular substance does not want the electricity to flow through it. All right? So it resists the flow of electricity. Now, I've been complaining that I don't have nearly enough time to get all my stuff in, but I can't resist. So, what did I find? All right. Star Trek. Stop talking. This is me talking to you. There was an original series of Star Trek with Captain James T. Kirk. But then in the late 90s, they created a new Star Trek show called The Next Generation. I think it's far superior. There was a captain, his name was Jean-Luc Picard. And they had an alien race that they battled called the Borg. The Borg were cyborgs. Does anybody know what a cyborg is? Yep. Well, that describes a Borg. Yep. Oh yeah, you're right. That's a Cyclops. What do you got?
Part of their body is machine or metal.
And the other part of their body is made up of some kind of organism. So it's a mixture of a machine and an organism. And the Borg were mean.
I am Locutus of Borg. Resistance is futile.
Did you hear that?
Your
Resistance is futile.
Is over.
Okay, the only reason I told you that was because the Borg would always say resistance is futile. And that's fun. And that's fun. Go home. It's on Netflix. All of them are. Star Trek The Next Generation, you want to look up the Borg. You want to do some homework on that. That has nothing to do with what we're doing today. All right. Except the fact that they use the term resistance. And I couldn't resist. All right. So what is resistance? Certain substances will prevent the flow of electric charges. And we call these things resistors. All right? How much an electrical component opposes the flow of electric charges. Now, this is true not just for resistors, which we know the symbol for, that squiggly, that squiggly thing, but it's also true for any wire or any substance. Any substance has a particular resistance value. Even the wires that we use for our circuits and the wires in your homes, the air has a certain resistance. Our bodies have a certain resistance. And again, it prevents the flow. If you want to draw that particular picture, again, it's to represent a section of a wire. So I just put an oval at one end, kind of like if you're drawing a cylinder of some sort. And then I just put the back end of the oval. It gives it a little bit of a three-dimensional structure. In this particular picture, the brown dots are representing copper atoms. So just put a regular array of atoms in your picture. And you can see I've got it on a little diamond shape, or perhaps a little bit of a squiggle shape there, or a greater than symbol, however you want to do it. And in my statement below, it says, as the electrons flow through the conductor, they encounter and collide with the atoms of the conductor. Each of these collisions results in electrons losing some of its energy. All right? So the electrons lose their energy as they collide with things. All right? So if you want to finish this picture off, I'm going to put here we'll put here a little dot here. This is going to be my electron. That's entering the wire on one side. And I'm simply going to represent that flow of electrons as if it bounces off of various atoms as it works its way down to the other end. In other words, it cannot move freely. Kind of like if you were to do some Christmas shopping, and maybe you were to start now, and you go to the mall Saturday morning at, say, 10 a.m. when no one's there. Easy to walk through the mall. No resistance. But if you then go to the mall on December 24th at about 5:30 because you haven't done some shopping, you may encounter lots of bodies, and as you attempt to do your shopping, you will run into traffic and you will encounter resistance. All right? It's the same idea. Okay? So all substances have a particular resistance. Some are greater and some are less, depending on their atoms and depending on the way their molecules are made up. And you guys don't know much about atoms and molecules yet, so there's not much more you need to worry about that. Some are greater and some are less. Now in my picture, I've only represented one electron, but as we probably imagine, within a wire, there will be billions and billions and billions and billions of them. Because remember, when we talk about coulombs, I believe the exponent on the number was 10 to the 17 electrons. So we're talking about a lot of electrons moving through the wire, colliding as they move. Okay? And this is true for wires. This is true for air, for wood, for all the stuff that we've already talked about. It's just another way of thinking about the way the electrons flow. Factors that affect resistance. Yep. How long?
I have like 3 words left.
Okay. Good to go? All right. Factors that affect the resistance in the conductor. Well, the type of material. Now, we've already used words to describe the way electricity flows through a substance. If a substance allows the electricity to flow very quickly, what did we call that particular substance? A substance that allows electricity to flow. What did we call that, Robert? So, would a conductor have low resistance or high resistance? Yeah, Tristan? Low resistance. A good conductor has low resistance because it does not resist. So we would call this a conductor. All right? Yep. Correct. High resistance would be an insulator. That would be things like air and rubber and wood and us. All right? Medium resistors in a circuit, we call it a resistor. So that symbol that we use in our circuit that has this medium resistance that we sometimes need in our circuit are called resistors. Examples of stuff that are good conductors. Cu. Do we know what Cu is? Yeah? It's copper. Cu is copper. One of the best conductors when it comes to metals, Au. What's Au? Yep. Oh, nope. Close. But no cigar. It starts with the A, but nope. It's a tricky one. It's gold. Au is gold. All right? Medium resistance, carbon. Carbon is used very often. C. I could have used C. And you know what? Aluminum. Al. Aluminum is one of these medium guys. Insulators, we're talking about things like rubber. And I'm just going to put an et cetera there, because we've discussed that. Okay, so different materials conduct or resist differently. Number 2, the length. Here I've got a stretch of wire. This is called nichrome wire. It's actually a medium resistor. It's a mixture of nickel and chromium. And I've got a big long length of it to illustrate to you how the resistance changes. I can set my multimeter to measure resistors. All right? I haven't told you what the unit is yet, but we can set it to do that. Again, I need some eyes on this, and it never stands up very well for me. Come on, Soap. Do your job there, Soap. All right. I'm going to be in trouble, though. Well, what do we think? Let's think about this. I've already drawn what happens to the electrons as they, fall through the wire. How is the resistance going to be affected if I've got a short chunk of wire versus a long chunk of wire? What will happen to its resistance, do you think, if it's a really long piece? What do you think? More resistance. It's going to encounter more atoms to bump into. If I take my 2 probes and touch them on the wire, can we see what it's reading there? 0. Oh, sorry, it's not. It's the decimal's in the other spot. It's about 1.9. It's about 1.9. The decimal's right after that. If I move my way all the way down to here, what did we do? 3.2. We went from about 1.9 to 3.2. The longer the wire, what am I putting? Larger, greater, however you want. Higher, doesn't make any difference. Whichever word you spell the most effectively. Okay? The longer it is, the greater the resistance. Cross-section area. That describes how big or fat the wire is. Whether it's a big fat wire with a big cross-section area or a skinny little wire with a small cross-section area. As the area of the wire increases and gets bigger, what do you think happens to the resistance? Yeah, it indeed decreases. And again, it's like walking through a hallway, like I said at the mall. Walking through a busy science hall here, yeah, not too bad. You can usually get around people. But if you're going down that funny little back hall at the gymnasium, you know what I mean, going to the music room, you know, the skinny little hall there, you run into people coming the other way, forget about it. Resistance. You got 2 or 3 people in there. If they're not standing on the right and left, it's chaos. Same idea. A skinny little wire will have greater resistance. Temperature. What does an increase in temperature do to the atoms of a substance? If a substance is hot, what are the atoms doing, Robert? They do spread out, correct. But it's for this reason, and I'm looking for a slightly different explanation. Yep, Danton? They move back and forth. They're vibrating. So if you're an electron and you're trying to get down the wire or the hallway, and instead of everyone standing still, they're moving back and forth like this on you, what's going to happen to your ability to get down the hall? Is it going to be easier or more difficult if they're moving back and forth? What's going to happen? Going to leave? More difficult, because you think you've got a good path, and then all of a sudden an atom is in your way, and you encounter resistance. As the temperature of the wire increases, the resistance, what's going to happen to its resistance? Yep, go ahead. It increases. Increases. And I just scribbled that, made a mess out of it. That says increases, for those who care. All right, now at this point, I had planned on showing you some resistors and showing you how, for a carbon resistor, which is what we're going to use, carbon resistors like this, how on the resistors they've got a color band that indicates what their resistance is. Because I want to keep going, and tomorrow's Take Our Kids to Work Day and all this other exciting stuff, and I got to move my lab back, I'm not going to bother with that. It's not that important. However, though, you use this chart to determine the value of the digits and a multiplier, and ultimately it tells you what that particular resistance is. I'm going to continue now on to discard. I'm going to continue now on to my next PowerPoint, which describes the calculation of resistance. All right? So we're continuing on. You can just keep writing. And what we want to do is we want to be able to do calculations on resistance. So again, we're going to be having another equation here in a moment. And we're going to ultimately be doing some calculations using that equation. And then on Thursday, we will do an experiment where we will test this law. Okay? On Thursday, because tomorrow is Take Our Kids to Work Day, so when we come back on Thursday, we'll be doing our lab. So resistance calculations and Ohm's law. Now, interesting little word here, Ohm, last name of a scientist. I don't know the dates in which he was doing this work, but he's the scientist who determined the relationship between volts, amps, and the resistance of a wire. And we call this relationship Ohm's law because he discovered it. All right, now there it is right there. And you can see there's another equation. And I'm hoping you're noticing that they look very familiar. That they all have a single number on the left and a fraction on the right. Yep,
It's just I.
it does. Our V and our I's are the same as we've been learning. You bet. That's correct.
Well, now we know what it is.
Lots of math. The voltage across a resistor divided by the current through the resistor is constant. So if we know the voltage that's being dropped at the resistor, and we know the current that's going through the resistor, we can do this calculation and we can find this property that we call the resistance. If you put more batteries into the circuit and you increase the voltage, you will automatically increase the current. It's as if the voltage is pushing the electricity through harder. Okay? It makes it run faster. If you decrease the voltage, it pushes less hard and the current flows less. All right? It's very much like water and pressure. How many people know what a high pressure sprayer is? Where's all of our good farmers out there? Anybody? Any of our good farmers? Anyone? Jenna? No, that's because you stay inside. You're going to learn about a high pressure sprayer tomorrow. I'd take our kids to work day. Excellent. If you've got a high pressure sprayer and you don't have the big motor on, there's just a little bit of water trickling out. It trickles out slow. Hold on one second. If you turn on that power, it pushes really hard and the water comes out with great speed. It's the same thing. If you've got a low voltage, that's like it's not pushing hard, the current moves slowly. You put lots of volts behind it, it pushes hard, the current moves fast. Yes, Danton?
So, one time, actually, some gravy was one of those.
Oh, excellent. Oh, it'll put a hole right in your hand.
I know, I was actually really surprised that they on.
Oh, yeah.
So, yeah, so, but it was great when my hand was on it, and a huge cut in my head, right in the middle there.
Okay. I'm just covering my microphone. We brought in family members. That's okay. I'm just kidding. All right. Let's do the calculation. Or let's do the rearrangement. V. We've seen this. Volts. Measured in?
Volts.
Yeah, that's a trick question. Volts are measured in volts. I. What's it stand for? That's the unit. Amps. What's the property called? The current. Current measured in amps. R. R is the resistance. Now, the scientist's name was Ohm.
Is it ohm?
It's measured in ohms. But we don't write the guy's name out. So we use, in this case, a Greek letter that looks like a horseshoe.
I've seen that.
Yep. That is a Greek letter. Does anybody know the name of that Greek letter? Robert? It's an omega. Get it? Omega. So it's an omega that stands for ohms. Let's keep going. Come on, folks, let's keep going. What if I wanted to rearrange this and I wanted to get V by itself? Okay, what if I want to rearrange it? I want to get V by itself. What is it? RI, correct? We typically write it IR. That's just the way I've always learned it, but it doesn't matter. You did a great job. No, you did fabulous. And what if I wanted, what's the only one I haven't got by itself? I, what's it going to be? What's it going to be? Yep. V over R. Excellent. Now, you know what? Most of you are starting to get this, but there's a few of you that are still struggling on rearranging it. I'm going to show you a little shortcut that one of your teachers may have shown you before. The math people don't like us showing you this because they want you to rearrange it properly. But let me show you how this works. Notice in all of our equations that when we have the fraction, there's always the same thing on the top. What's always on the top in this particular version that we've got here? When I've got the fraction, what's always on the top, Rachel? V. V is always on the top. This little trick involves writing a triangle like this that's broken into 3 blocks. If you are no good at rearranging things, write this down. Because the V is always on the top, I'm going to put the V on the top of this triangle. Okay? And now I have my other 2 letters that have to go in. Notice that in my original form, the I is on the bottom, so I'm going to put this I over here on the right-hand side. There's my V over I. Now I'm going to write the last letter there. Now, how do we use this particular trick? I'm just going to explain it. For the equation that you want, cover up the thing that you want to solve for. In the first equation, it's R. I cover up R. What am I left with? Yep, V over I. If I want to solve for V, I cover it up. What am I left with? R times I. And if I want to solve for I cover it up. That's not math. That's a trick. Math teachers want us to teach you math, but some of you are not good at math, so you use a trick. You can do the exact same thing with all of the equations I've taught you. In the current equation, I equals Q over T, what will go on the top of your triangle? What will go on the top of your triangle? Rachel? Do you like rearranging equations, Rachel? Then you really want to be able to figure this out, don't you? What did I put on the top of this triangle, Rachel? Why? Because it's on the top of everything. If I'm using my equation, I equals Q over T, what am I putting on the top? Good job. And the rest go on the bottom. If I'm using my equation, V equals E over Q, what's going on the top, Parker? E. And everything else goes on the bottom. Everybody catch that? On tests, I am not giving you the triangle, ever. I will give you the original versions of the equation. It is your responsibility to figure out how to make your own triangle if you need it. Everybody catching this? Okay. I am going to go ahead past this slide. This slide talks about what graphs look like if we're doing Ohm's law. I'm going to go past it, and I'll come back to it before we do our experiment. And I'm going to go straight on to the questions because, well, we've spent a lot of time figuring out how to get equations. Let's practice our questions. Thank you, Jess. Your favorite student status is slowly increasing. Good job.
Wait, there's a favorite student?
No, there isn't. Just write the question. Jay, your favorite student status is on the way down. You see? It's an up and down scenario. There isn't a favorite student. There are some slightly more annoying than others students. Just write it. Just write the question down.
Do you have your microphone still on?
I do. I'll whisper it, and you guys you'll have to go back and watch the video. I'm going to go with my slightly annoying student. What am I going to go with? This is a trick. Yes. A random story. You just did that to stir that up. Here we go. Grade 8. Grade 8. But you're behaving as grade 8.
I'm not.
You're not. As a group, we've got a lot of grade 8 action going on here today. But that That shirt cancels everything out. Go Leafs, go. All right. Remember how we do this. Now notice that we're talking about a circuit. We're talking about resistance. We're talking about that squiggle, but we don't need that right here to practice our calculations. Voltage drop, V, 2.5 volts. That's how many volts were left in the resistor. The current going through the resistor, 0.264 amps. So, again, if you know your units and you know what they represent, you've got the two knowns. Now you've got your triangle. What are we trying to find in this one? Jess, what do you got? R. And what's the equation for R? Well, cover it up in the triangle and tell me what is what. Robert? V over I. Robert's loving this. V, 2.5 volts over 0.264 amps. I need a number, and I don't want the whole string across your calculator. I just want about 3 things. What do you got there, Travis? 9.46 unit. What's the unit called, Robert? Ohms, which we will write as omega. If, say, on a test, you forget the symbol for ohms, you could write OHM, would be fine. All right? Yep. Okay. Yes? O can be misinterpreted as zeros. So you'll find that we very rarely use O in physics and that type of thing. It can be confused for zeros. It can be confused for an oxygen atom. There's lots of things it can be confused for. What are you telling me? Milliamps that we've got to convert. Milliamps. Come on, folks. Write it down. Useless as a calculator? Yeah. It is indeed.
Well, no, like, it has a calculator, but...
What are we asking? Not 6, just 3. Yes, question.
No.
Oh, running to the back. I am recording. Here, I'm going to put out this.
No,
Oh, goodness. There is lots of homework that is on the back of this slide. It's on Google Classroom. Make sure you work on it. Okay. 525 milliamps. What is that? Which symbol is that? What thing is that represent? Yep. Tristan? I. Now, milliamps, not useful for us. So, we did some practice of this when we did current. It's just like millimeters, right? There's 1,000 millimeters in a meter. Same thing here. There's 1,000 milliamps in an amp. So if I have 500 milliamps, how many amps is that? Yep, Denton? Correct. We move our decimal place 3 spots, representing dividing by 1,000. We divide that by 1,000, which moves that over that much. 0.525 amps. Excellent. .5 volts. V. Again, we're getting the resistance. Same question as the last one. The purpose of this question is to show you what to do if you have milliamps. Because when we do our experiment in the next day, we will have some that say milliamps, and we've got to move it over. R equals V over I, 3.5 volts 0.525 amps. Again, this is where I'm deafened by the sound of calculator keys clacking up against your fingers as you feverishly put it in and then put your hand up. Guess what do you got? So we'll round one of those to the 7. We don't need to go 66666, right? And what's the unit? No, it's pronounced ohm, not but that was pretty close. Ohm, not That's close, but it's not exactly correct. I know. Not likely. Oh, yeah, for sure. Yep. All of the Greek letters that we use in physics, we can find. It's not a key. It's a special symbol that I've got to go and find. But it's not a key. It's a special symbol. In physics, you will learn all kinds of interesting ones. Well, I already told you that there's a mu, right, for micrometers. That's a Greek letter. That's a Greek letter M. It's a lowercase m. That ohm is a capital ohm. Can't remember what a small ohm looks like. Never used a small ohm. Yes.
Why Greek letters?
Well, what other letters would we use that aren't regular, I guess, like what? Well, like what? Well, I don't know either. What's that? That's true. Yeah, you could use a completely different, Mandarin or, because it's historical and Greek and Latin were languages that scientists had to know. Like years ago, they had to write their reports in Latin, right? So Sir Isaac Newton's laws were written in Latin. So Latin and Greek are very important. I'm going to continue with this. A 150 ohm resistor, R equals 150 ohms, has a voltage drop, V, of 0.75 V. Determine the current through the resistor. What is my equation? Rachel, what's the equation going to be? Nice. 0.75 volts over 150 ohms. Do you have an answer, Rachel? Well, I'll tell you whether it is or isn't. 005. Do you have any other digits behind there? There's nothing else behind it? That's fine. What's the unit for I? What's the unit for I? A. Amps. Okay, yep. In scientific notation? So it would have written it as 5 times 10 to the -3 amps. And both of those things are correct. You have yours set on scientific notation. I don't care. This is science. Scientific notation is good.
Yes, I'm wrong.
Is this the last example?
No, there's number 4, but
There is number 4. Yeah.
Okay, you can go now. I unlocked.
You unlock.
No, I guess I don't.
By the way, folks, when I post the videos, I also post the PowerPoint with all the writing on it that I do. So you'll notice if you go back, you'll see the PowerPoint that's blank, and you'll see the PowerPoint that says with notes. It means I've added the notes, so you can see the writing if you missed some of it, okay? All right, you can always go back and check it. We good to go? Jamie's just finishing off. All right, click and click. And this is the last one. Yeah, this is the last one. By the way, I think number 2 or 3 is the graph. You can make the graph, but I'm going to have to tell you how to analyze the graph. It's a slope one, and we jumped past through the slope thing. But number 2, you said 3 is? 3 is the graph? 2 is the graph.
3 is supposed to fill in the blank, or 3.
You should be able to calculate. I think there's just one graph that we asked you to make. So you can make the graph, but I won't be telling you how to analyze it until the
2
next day.
and 3 are about the graph.
Right. So if don't worry about the graph ones. Yep. Yeah, you can go. You can go. Okay. So 2 and 3, don't worry about 2 and 3. If you make the graph, I'm going to get you to analyze it eventually, but I'm going to let you work a little bit on these. So 2 and 3 are the graphs. I'll put a little note on the back end. The resistance of a motor. Now, we've drawn that picture for resistance, that squiggly line, but again, all electrical objects will have a certain resistance. Lamps or lights will have a resistance. LED will have a resistance. Goodness, the wires even have a little bit of resistance. So we can talk about the resistance found in a motor. That makes good logical sense. And you can see there it is 230 ohms. The current through this particular motor is 1.2 amps. Determine the voltage drop. Again, it just means that that voltage was dropped off in this motor. What's the equation? What's the equation? Chloe, what's the equation? She wasn't ready. Use that triangle. Come on, use that triangle. What is the equation? V equals I times R, or V equals R times I, it doesn't matter. Again, we should be doing the math, right? If we're doing it properly, we're going R is equal to V over I, and as I've been telling you, that I goes up there and becomes a multiplication, and that gets us V equals IR. That's to make the math people happy. 1.2 amps. It doesn't matter the order. I was going to put the R versus the I. It doesn't make any difference. And 230 ohms. And how many volts were dropped off there? Robert, what do you got? 276. 276. And the unit is volts. 276 volts of energy was dropped off. Okay? So, our homework for today, and you got about 20 minutes, 1 to 9, and I'm going to say, don't worry about 2 and 3. Is that what you're telling me? 2 and 3?
2 and 3, yeah.
2 and 3. Don't worry about 2 and 3. Okay? That involves the graphing. You could make the graph, and by the way, the resistance is simply the slope of a VI graph, but that I jumped ahead on that slide. Yes. I'm still making movies. Yep. I think it asks you which is the best way for you to understand Ohm's law. Is it the graph, or is it the equation, or is it the definition of it? Obviously, the graph isn't very good for you because you don't know the graph one. Yeah. Let me finish this particular thing here. If I could see what the heck's going on here, and then I'll do it. Okay.